Hello, this is Professor Dan Kernler again, and in this video we are continuing in section 17.3 where we're looking at conservative vector fields. And in this video we're going to get a series of theorems that are going to be really valuable about conservative vector fields and how that can help us with some line integrals. So we're going to start with an example. We're going to do this a little differently here. I'm going to do part of this and then I want you to pause the video to continue the rest by yourself. That's I think how this is most effective. So what we're going to do is we have a field. We're going to pretend that this is a force field, which is always fun to say. So it is a field of different forces that are on a particle. And we're going to have the particle move along three different paths. And we want to find the work done. So we know the work done is the line integral over the path of the force field times dr. And so let's see here. Here we have our path. R is equal to, for this first one, t and 1/2 t. So r prime will be 1 and 1/2. So this will be the integral. Looks like t goes from 0 to 2. The force will be 2 times x, which will be 2 times t. And then y is 1/2 t. And the dot product with dr, which will be r prime 1 1/2, and then dt. Okay, the dot product there gives us, what does that give us? 2t plus 1/4 t. And that'll give us the integral from 0 to 2 of 9/4 t dt, which gets us 9/8 t squared from 0 to 2, which would be 9/4. So let me scroll up there. 9/4 9/8 times 4 minus 0. And so we end up with 9/2. So 9/2 is that first, the amount of work done. We don't have any units here, but that's the work done moving a particle along this path through, that's the work done by the force field as the particle moves along that path. So what I would like you to do next, something we have not done in this series of videos yet, I'd like you to pause and try this again on the next two different paths this time. Should take you about 5 minutes maybe, and see if you can find the work done by the field moving along these different two paths.
A few moments later.
All right. Hopefully you did that. If you had, you should have found out that, in fact, this one will give you 9/2, 4.5. This one also gives you 9/2. You'll also notice they all start at the origin and end out here at 2, 1. So they all have the same starting and ending point. 2, 1, starting at the origin, start at the origin, and at 2, 1. So this isn't a proof, but it seems to be here that the work doesn't seem to matter what path you go on. It just really matters on where you start and where you end. So we're just going to write here, it seems as though the work is independent of the path taken from A to B. Now we didn't try an example with a different starting and ending point. All of our three examples had the same starting and ending point, which is worth noting. Okay, so the next thing here, boy, this seems kind of important. So important that it is titled the fundamental theorem for line integrals. So we're going to do a little derivation here, a short proof. Suppose we have phi, which is a differentiable potential function defined on a region R, which is three-dimensional. So we have phi is a function of x, y, and z. We're going to suppose we have the curve C that's given parametrically to us. And t goes from A to B. And then we have position vectors at A and B represent the points capital A and capital B. Okay, well, let's take the derivative of phi with respect to t. Well, we would need the chain rule for this. That would be the partial derivative of phi with respect to x times the derivative of x with respect to t, plus the partial derivative of phi with respect to y times the derivative of y with respect to t, plus the partial derivative of phi with respect to z times the derivative of z with respect to t. And now you'll notice here there are these three multiplications. We could write this as a product, a dot product of two vectors. All the partial derivatives of phi, the dot product with all the derivatives of x, y, and z with respect to t. Well, those should look familiar. The partial derivative of phi with respect to x, with respect to y, with respect to z, that's the gradient, right? That's the gradient. That's the gradient of phi. And then we have this dx dt, dy dt, dz dt, that's r prime. Well, what if we let a vector field, some field, let's let the field be this gradient of phi. So this will be noted, the phi, the dot product with r prime of t. Okay, well, in that case, if we were to find the line integral over our path C of the dot product between f and dr, whoa, this would be equal to the line integral, or sorry, the integral from a to b of our field f and the dot product with r prime of t dt. But that dot product is the derivative of phi with respect to t. So this is the integral from a to b of d phi dt dt. Well, that looks familiar. I mean, it's a weird symbol there with phi, but that's the integral of a derivative. That's the fundamental theorem of calculus from Calc 1. That's phi evaluated at the upper limit minus phi evaluated at the lower limit. Sorry, I'm misspoke a little too soon. So it's basically that, but it is phi evaluated at, now I'm integrating here, these a's and b's are t's, and phi, of course, is a function of x, y, and z. So we would need to find phi at that corresponding x, y, and z value. So it's phi at the point B. That point B is x at B, y at B, this is lowercase b, and z at b. Those are the coordinates when t is b, minus phi at a. Similarly for a. All right. Okay, so this is the fundamental theorem for line integrals. If R is a region, and it can either be in R2 or R3 in 2 dimensions or 3 dimensions, and phi is a differentiable potential function, if your field is the gradient of phi, in other words, your field is conservative, then the line integral of your field dot product with the tangent vector, remember that line integral derivation, which is equivalent to the version we just did, the dot product of field and dr. You can simply evaluate the potential function at one endpoint and subtract evaluating the potential function at the other endpoint. It does not matter what happens between and how it gets from point A to point B. All that matters is what is the value of the potential function at B subtracting what is the value of the potential function at A. So this is the fundamental theorem for line integrals. Okay, so that's super helpful. So why did we get the same answer for each of the work calculations? Let's check back there. You'll see we have the field 2x comma y. Well, if we take the partial derivative of that f the x component there with respect to y, the cross one, that's 0. The partial derivative of the g with respect to x, also 0. So this field is conservative. Which implies there is can't write here. There is a phi such that the field is equal to the gradient of phi. Well, if our field 2x comma y is equal to the gradient of phi with respect to x, phi with respect to y, we can do a quick derivation here. Phi must be equal to the integral of 2x dx, because that's the derivative with respect to x. So that's x squared plus some function of y, we'll call it c of y. If we take the derivative with respect to y, we get c prime of y. That must be equal to y. So that means phi, I did not leave enough space here, is equal to x squared plus, if we integrate that, I don't have space for that, but that would be 1/2 y squared. And so if we evaluate phi at the one endpoint, which was 2, 1, what would that be? 2 squared is 4 plus 1/2, so that's 9/2. And phi at the origin is 0, so when you subtract them, you get our 9/2, right? That was the 9/2. So it doesn't matter what path it traveled on, because the field was conservative, because there's some potential function where the field was the gradient of that potential function. It didn't matter what path we went on, we were always going to get the same answer. The only thing that mattered was the value of the potential function at 2, 1 and the value of the potential function at the origin. So here's another note here. If a vector field f is conservative, then this line integral is dependent only on the endpoints of the path. So here we have an example. We're supposed to evaluate the line integral of this field where C is a piecewise smooth curve. So we don't know what the curve is, but we just know it starts at 1, 5 and goes to 3, -1. Well, if we take the partial derivative of f with respect to y, that's 3y squared. If we take the partial derivative of g with respect to x, that's 3y squared. So our vector field is conservative. And then from example 1, we actually know the phi. I wrote it down here. It is xy cubed minus x squared. All right, so let's find phi at the end point 3, -1, which will be 3 times -1 cubed minus 3 squared. So that would be, what, -12? And then phi at 1, 5, where it started, would be 1 times 5 cubed minus 1 squared. So that's -124. Therefore, the line integral will just be phi at 3, -1. I didn't really leave enough space here. Let's see if I can write it smaller. Phi at 3, -1 minus phi at 1, 5, which will be, let's see here. Actually, no, that's not -124. That's positive. I'm getting ahead of myself because I knew the answer was negative. So that's -12 minus 124, and so we get -136. All right. Again, we didn't even need to know the path. All we needed to know was that the field was conservative. We have a piecewise smooth curve from 1, 5 to 3, -1. So all we needed to do was substitute in those points into our potential function. Now here's a question. What if we changed the orientation and went backwards? Well, then the line integral would be phi at 1, 5 minus phi at 3, -1. So then it would be 124 minus -12. Then it would be positive 136. So the direction that you travel on your paths is going to be important. This is going to be important as we progress into some of the later sections as well. All right, here's another theorem. We're not going to prove this. We're just going to state this. If your field F is continuous on an open connected region R, then the line integral is independent of path if and only if the field F is conservative. So if it's conservative, it will be independent of path. And if it turns out that your line integral doesn't depend on the path, then the field must be conservative. Okay, we're going to finish with one last set of examples and a couple of theorems. So we are going to do this example, the same field, and we're going to try following the path from 0, 1 to 1, 0 along the unit circle. And we're going to try it 3 different ways just to show that we will get the same thing all 3 methods. We have 0, 1 to 1, 0, where the unit circle, that was not very circular, not much better, 0, 1 to 1, 0. So this is the direction we're going. Let's see here. Method number 1, let's parameterize the path. So this would be like the first line integrals that we did in section 17.2. Well, it's on the unit circle. So cosine t sine t. Well, I guess that's a problem there. Cosine t sine t starts at 0 and 1, 0 and goes up. So we need to reverse that. Let's have it be sine t. Ooh, is this going to go in the right direction either? I don't think that's going to go in the right direction either. Let's see here. Sine t cosine t. When t is 0, oh yeah, that'll start at 0, 1. Yep. And then when t moves to pi over 2, then it'll go to 1, 0. Perfect. So that's 0 less than or equal to t less than or equal to pi over 2. So by switching the x and y of the usual unit circle, it will still be the unit circle. It will start at a different point, and it will have the opposite orientation than what we're used to. So this will get us what we want. Okay, so we're going to do the line integral. Okay, we need to find r prime. We can just do that in line here. So this is going to be the integral from 0 to pi over 2. My field, this is going to be a little gross, y cubed, that's cosine cubed t minus 2 times sine t. All right, and then 3x y squared, cosine squared t. Okay, and then dot product with r prime, which is cosine t negative sine t, and that's going to be dt. We can simplify that. We are not actually going to compute this by hand. This would be pretty gross. What does this end up being? 3 sine t cosine to the 5th t? No. Yeah, no. Hold on, back up. So I need to multiply those. I was multiplying times. We need to multiply by cosine. So that'll be cosine, oops, not a vector anymore, cosine to the 4th minus 2 sine t cosine t. And then multiply by negative sign, so negative 3 sine squared t cosine squared t dt. Looks pretty gross. We'll say if you want to just try this, you could use a calculator to do that. You actually get negative 1. You get negative 1. It's an integral you could do. You'd have to do, it would not be fun. We'll just put it that way. We'd take the rest of this page to do it. Okay, second, let's just change the path. We know that this field is conservative. We've already shown that. So let's do a different path. Yeah, you said I had to do the unit circle, but I know the field is conservative, so the path doesn't matter. So I can do a different path. I'm just going to make my path simple. I'm just going to go a line. Right? Why not? So r of t will be, well, let's go t from 0 to 1, and then y would be, what would that be, 1 minus t? And t goes from 0 to 1. So what I did there is basically just make the line y is equal to negative x plus 1, or 1 minus x, and then just make xt, and then make y, what the value of the function would be, 1 minus t. Okay, so much simpler function. Now the line integral becomes, let's see, this is going to look a lot better, integral from 0 to pi over 2, and we have our field, which is y cubed, still a little gross, 1 minus t cubed minus 2x, so minus 2t, and then 3xy squared, 3t, 1 minus t squared, okay, and then the dot product with the derivative of that, well, that's so r prime of t, that's just 1 negative 1 dt. That looks a little bit better. If you want to take a moment, do some algebra here. It's not really worth our time in the video. If you multiply all of that out, I have it written down here, you get 1 minus 8t plus 9t squared minus 4t cubed dt. Nice Calc 1 integral. What would we get there? We would get t minus 4t squared plus 3t cubed minus t to the 4th from 0 to pi over 2. Oh, sorry, what is 0 to pi over 2? That's the old one. That's the old one. We have a new path. We have a new path. T is from 0 to 1 on this path. And so we end up getting, let's see, what do we get? 1 minus 4 plus 3 minus 1 minus 0, and we get negative 1 again. I'm kind of waving my hands at some of that, but it's just algebra in the middle there. And you can see there at the end, we do indeed get negative 1. Okay, last method. Well, we know f is conservative. That implies that our field f is the gradient of some phi function. And we already did this. We already know the phi function. We have it up above previously. Where did that one go? Here it is again, xy cubed minus x squared. And so the line integral can just be phi at the ending point, phi at 1, 0 minus phi at 0, 1. How easy is that? That 1, 0, that's 1 times 0 cubed minus 1 squared, minus phi at 0, 1, 0 times 1 cubed minus 0 squared. You get a negative 1. So, the benefit of this theory, of this fundamental theorem of calculus, is if you can do a little work to find that potential function, you don't have to do a path, you don't have to do any crazy integrals. You can just evaluate that potential function. You do have to find the potential function, but you can just evaluate that potential function at the two endpoints. Okay, last thing here. What if we evaluate this on one complete rotation of the unit circle? So wherever we want to start. Say we start here, we go all the way around. All the way around. So again, we know that the field is conservative. So that means it would be phi at the endpoint, 1, 0, minus phi at the endpoint, 1, 0. And so we would just get 0. So this is actually true if we have a simple closed curve. If the curve goes all the way around and gets to 0, if your field is conservative, then your line integral will be 0. So let R be an open connected region. This is either in 2 or 3 dimensions. If F is a conservative field, sorry, this is actually an if and only if statement. It goes both directions. So F is a conservative field if and only if the line integral of F over that closed curve is 0 for all simple closed curves. So this is both ways. Now, you're not going to prove it this way, but if the line integral is 0 for all simple closed curves, then the field must be conservative. And then if the field is conservative, the line integral must be 0 on all closed curves. So that's the method, that's the one we will use most often. So final theorem here, and these are just some equivalent facts. The field is conservative. The line integral doesn't depend on the path. And then third, the line integral will be 0 for all closed paths. Those are all equivalent statements. There is one more page in the notes, but this is kind of an extra little fun thing from physics. So we are not going to do that in this video. And that is it for section 17.3 about conservative vector fields.